There was a time when the newspapers said only 12 men in the whole world understood the theory of relativity. I never believed that. There might have been a time when only one man did, because he was the only guy who caught on before he wrote his paper. But after people read Einstein's paper, plenty of people understood relativity. Certainly more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. Now, I said that. I meant it. And I said it in front of a room full of very smart people at Cornell during a set of lectures in 1964. And you might think, well, that's a strange thing for a physicist to say, because here I am, a guy who uses quantum mechanics every single day. I calculate with it. I make predictions with it. I built a good chunk of my career on it. So what do I mean? Nobody understands it. That's the puzzle I want to investigate with you today. Not quantum mechanics itself, not yet, but what it means to say that nobody understands it. Because I'll tell you something, most people who hear that quote walk away with completely the wrong idea about what I was getting at. And the wrong idea they walk away with tells you something very interesting about how the human mind works, and about what we expect from nature, and about the deepest trouble in all of physics. So let's be detectives. Let's treat my own words as a crime scene. What did I actually mean? Let me lay out the suspects one at a time, and let's see which one holds up. And I'll tell you right now, the answer we find is going to lead us somewhere unexpected. Somewhere that connects to the biggest unsolved problem in all of physics. But we have to earn that. First, the suspects. The first suspect is the most popular one. Almost everyone grabs this one first. They hear, nobody understands quantum mechanics, and they think, oh, he means the math is too hard. The equations are too complicated. It's all Greek letters and abstract nonsense, and you need a genius brain to follow along. And look, I get why people think that. If you've ever glanced at a quantum mechanics textbook, you've seen the wave functions, the Hilbert spaces, the Brockett notation, the operators. It looks like an alien language. So the natural assumption is that Feynman, good old plain-talking Feynman, was just admitting that even for the experts, the mathematical machinery is overwhelming. But that doesn't hold up, not even for a second. Because here's what I know about the math of quantum mechanics. It works. It works spectacularly well. You write down Schrödinger's equation, you solve it for a hydrogen atom, and out pop the energy levels, and those energy levels match the lines you see in the spectrum of hydrogen to an absurd number of decimal places. You use quantum electrodynamics, the theory I worked on myself, and you can calculate the magnetic moment of the electron to better than 10 decimal places. And the experiment agrees. 10 decimal places. That's like predicting the distance from New York to Los Angeles and getting it right to the width of a human hair. So the math isn't the problem. The math is, if anything, the one part we're completely confident about. Physicists use this math every day and it never lets them down. Chemists use it. Engineers building transistors use it. The entire semiconductor industry, every transistor ever built depends on quantum mechanical calculations that come out right. If nobody understood the math, none of that would work. But it does work, every time. Suspect number one, the math is too hard, doesn't fit the evidence. Throw it out. All right. Suspect number two, maybe what I meant is that we don't have enough experimental data. Maybe quantum mechanics is like a half-finished map. We know some corners of it, but there are big blank spaces. Maybe I was just saying, look, we haven't tested it thoroughly enough, so we can't claim to really understand it. This one doesn't survive either. In fact, it's even worse than the first suspect. Quantum mechanics has been tested more thoroughly than any theory in the history of science. Not just tested, brutalized. For decades, people have tried to find an experiment where quantum mechanics gives the wrong answer. Not because they hate the theory, but because finding a crack in it would be the most important discovery in physics. It would win you the Nobel Prize so fast your head would spin, and nobody has found that crack, not in 90 years of looking. Every prediction quantum mechanics has ever made, when calculated carefully and tested honestly, has come out right. Atomic spectra, molecular bonds, superconductivity, lasers, the behavior of semiconductors, the properties of superfluids, the Lamb shift, the anomalous magnetic moment, the Casimir effect, tunneling through barriers. Every single one. In the late 1970s and the 1980s, people tested something called Bell's inequalities. Let me tell you briefly what that's about, because it's important. The story goes back to 1964, when a physicist named John Bell, an Irishman working at CERN, asked a very sharp question. He said, suppose quantum mechanics is wrong, and underneath all this probability business, particles really do have definite properties all along. Suppose there are hidden variables, secret little notes each particle carries in its pocket, telling it how to behave in every possible measurement. If that were true, what would we expect to see? And he proved, mathematically, that any such hidden variable theory would have to obey a certain inequality, a limit. The correlations between measurements on two separated particles could never exceed a certain value. Then he showed that quantum mechanics predicts correlations that violate that limit. Quantum mechanics says you can get correlations that are stronger than any hidden variable theory allows. So the question became, which is right? Is nature playing by the hidden variable rules, or by the quantum rules? Starting in the early 1980s, Alain Aspect and others ran the experiments. They measured correlations between pairs of photons, separated by enough distance that no signal traveling at the speed of light could pass between them during the measurement. And the results violated Bell's inequality. They matched quantum mechanics perfectly. Nature is as strange as quantum mechanics says. There's no comfortable, hidden, common-sense explanation lurking below. Not unless you're willing to accept something even stranger, like influences that travel faster than light, or a universe where the future affects the past. So suspect number 2 is dead. We have mountains of data. More data than we have for almost anything else in physics. Lack of evidence is not the problem. Let me bring in suspect number 3. This one is subtler. Some people hear my quote and they think, well, that's just Feynman being humble. Or Feynman being cute. He's a showman. He likes to say dramatic things. And nobody understands quantum mechanics is a great line for a lecture. Gets a laugh. Puts the students at ease. Don't worry, kids. Even the great Feynman doesn't get it. And I'll admit there's a grain of truth to this. I did want to relax the audience. I was about to describe some very strange things, and I wanted people to stop trying to force those things into familiar boxes. I literally said right after that line, do not keep saying to yourself, but how can it be like that? Because you'll get down the drain into a blind alley from which nobody has escaped. So yes, there was a pedagogical purpose, but if you think the whole thing was just a rhetorical flourish, you've missed it. You've missed the most important word in the sentence. And that word isn't nobody. It isn't quantum, it isn't mechanics. The word is understands. That's the real clue. That's where the case breaks open. Everything hinges on what you mean by understand. Let me show you what I'm getting at. And to do that, I need to take you through the single most important experiment in all of physics. The experiment that, more than anything else, reveals why quantum mechanics is the way it is. The double-slit experiment, you've probably heard of it. But let me walk through it carefully because the devil is in the details, and the details are where the trouble lives. Here's the setup. You have a wall with 2 narrow slits in it. Behind the wall, you have a screen that can detect where particles land, and you have a source that fires particles, one at a time toward the wall. Start with something ordinary. Bullets. Imagine you have a machine gun that sprays bullets somewhat randomly toward the wall. Some go through the left slit. Some go through the right slit. The rest hit the wall and stop. On the screen behind, you get 2 clusters of bullet holes. One cluster behind the left slit, one behind the right slit. Makes perfect sense. Each bullet goes through one slit or the other and lands accordingly. Open both slits, and the pattern on the screen is just the sum of the 2 individual patterns. Nothing surprising. Now do it with water waves instead. You have a pond and you drop a pebble to make ripples. The ripples hit the wall, pass through both slits, and on the other side they spread out and overlap. Where the peaks of 2 waves meet, you get a bigger wave. Where a peak meets a trough, they cancel. On the screen, you don't get 2 simple clusters. You get an interference pattern. Bright bands where the waves reinforce each other. Dark bands where they cancel. Very different from the bullet pattern, but completely understandable if you know how waves work. All right, now the main act. Do it with electrons. Fire electrons, one at a time, at the double slit. Each electron hits the screen and makes a tiny dot. Just like a bullet, 1 dot, 1 electron, 1 click on the detector. So far so good. But here's what happens when you fire thousands of electrons, one at a time, and look at where all the dots accumulate. You do not get 2 clusters, you get an interference pattern. Bright bands and dark bands, exactly like the water waves. And that's already very strange, because each electron arrived as a single dot, a single particle. It didn't spread out like a wave. It went click. Right there, one spot. But somehow over thousands of individual clicks, The pattern that emerges is a wave pattern. So you might think, okay, maybe each electron is secretly a little wave, and when it hits the screen, the wave collapses to a point. Weird, but maybe I can live with that. But wait, here comes the part that really hurts. You ask, well, which slit did the electron go through? Perfectly reasonable question. It's a particle that made a dot. It must have gone through one slit or the other, right? So you set up a little detector at one of the slits, a tiny light, say, that flashes when an electron passes through. Now you can tell which slit each electron went through, and the instant you do that, the interference pattern vanishes. Gone. You get two simple clusters, just like bullets. Let me say that again, because I want you to feel the full weight of it. When you don't look at which slit the electron goes through, you get the wave pattern. When you do look, you get the particle pattern. The act of finding out which slit it went through changes the result. This is not a matter of clumsiness. It's not that the detector bumps the electron and ruins things. People have tried every conceivable way to be gentle, to minimize the disturbance, to sneak a peek without touching. It doesn't matter. Any method whatsoever that gives you information about which slit the electron went through destroys the interference pattern. The universe seems to have a rule. If you can know the path, no interference. If you cannot know the path, interference. And if you think that's strange, let me make it worse, because there's a version of this experiment proposed by John Archibald Wheeler that is even more disturbing. It's called the delayed choice experiment. Here's the idea. You fire your electron toward the double slit. You let it pass through, and then after it has already passed through the slits, you decide whether or not to detect which slit it went through. You make the choice late, after the electron has supposedly already decided whether to be a particle or a wave, and it still works. If you choose to detect the path after the fact, the interference pattern vanishes. If you choose not to detect the path, the interference pattern appears. The electron seems to have known retroactively what you were going to decide. Now, you have to be careful about how you describe that. It does not literally mean the future is affecting the past. But it does mean that you cannot think of the electron as having chosen a definite behavior at the slits. The electron does not become a particle at the slits and then stay a particle. It does not become a wave at the slits and then stay a wave. What the electron is between the source and the screen is not determined until the entire experiment, including your measurement choice, is complete. Wheeler used to say, no phenomenon is a phenomenon until it is an observed phenomenon. And he meant that quite literally. The experiment has no definite outcome, not even a definite past, until the measurement is actually made. If that doesn't bother you, think about it again more slowly. Now, sit with that for a moment, because this is where the trouble starts. In classical physics, the physics of everyday life, we understand things by building pictures, models, stories about what's happening when we're not looking. The ball is at the top of the arc. The planet is on the far side of its orbit. The gas molecules are bouncing around in the box. We have a mental movie of what's going on behind the scenes, and that movie is consistent, and it makes predictions, and those predictions match what we see. This is what understanding feels like. You can close your eyes and picture the thing. You can run the mental movie forward and predict what happens next. You have a mechanism, a story, a picture of what is going on. And the double-slit experiment says you cannot do that for quantum mechanics. Not because you're not smart enough, not because you need better instruments, but because there is no consistent classical picture of what the electron is doing between the source and the screen. Think about it. If the electron goes through one slit, you should get the bullet pattern, but you get the wave pattern. If the electron goes through both slits, well, how does a single particle go through two slits? And if you try to check, the pattern changes. The electron seems to refuse to have a definite story about what it did. This is not a failure of imagination. People have tried every possible picture. The electron is a particle that secretly goes through both slits. The electron is a wave that collapses when observed. The electron takes all possible paths simultaneously. The universe splits into two copies. Each of these ideas has been explored, debated, published, and picked apart by very brilliant people for the better part of a century. And none of them is universally accepted. None of them can be proven to be the one true picture. Because quantum mechanics, the actual mathematical theory, does not tell you what the electron is doing between measurements. It tells you the probability of where you'll find it when you look. That's all. And that's enough to make all those spectacularly accurate predictions I mentioned earlier. But it doesn't give you a picture. It doesn't give you a mechanism. It doesn't give you a story you can close your eyes and watch like a movie. And that right there is what I meant. When I said nobody understands quantum mechanics, I was not complaining about the math. I was not lamenting a shortage of data. I was not performing false modesty. I was making a precise statement about a precise problem. We do not understand quantum mechanics in the way we understand other theories. We do not have a mental picture of what is happening at the quantum level. We have rules that tell us what we will observe when we measure, and those rules work perfectly. But behind the rules, behind the calculations, there is no story, no mechanism, no picture that everyone agrees on, and that doesn't lead to paradoxes. Understanding in the deepest human sense means being able to say, here is what's happening and here is why. In quantum mechanics, we can say, here is what will happen, but we cannot say why, and we cannot say what is happening in between. That is what nobody understands. Now let me go further, because the problem is even deeper than the double-slit experiment suggests. The double-slit is just the doorway. Behind that doorway is a whole landscape of trouble. Consider measurement. In quantum mechanics, a particle can be in what we call a superposition. An electron spin, for example, can be in a state that is neither up nor down, but some combination of both. Not that we don't know which it genuinely is both, in a very precise mathematical sense. The amplitudes for up and down are both present. Then you measure the spin, and you always get a definite answer. Up or down, never both. The superposition is gone. You got one result. What happened? How did the superposition become a definite outcome? What is the mechanism? Schrödinger himself saw this trouble coming. He was one of the architects of quantum mechanics, and he was deeply uncomfortable with the implications of his own theory. So in 1935, the same year as the EPR paper, he cooked up a thought experiment designed to make the absurdity vivid. You put a cat in a box. With the cat, you put a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter clicks, the vial breaks, and the cat dies. If the atom doesn't decay, the cat lives. Simple enough. But the atom, according to quantum mechanics, doesn't have a definite state until you measure it. After 1 hour, the atom is in a superposition of decayed and not decayed. And since the fate of the cat depends on the atom, the cat is supposedly in a superposition too. Alive and dead at the same time. Now, nobody actually believes the cat is both alive and dead. Schrödinger didn't propose this because he thought it was a reasonable description of reality. He proposed it to show that something must be going wrong when you extend quantum rules from atoms to cats. Somewhere between the atom and the cat, the superposition must resolve into a definite outcome. But where? And how? That is the measurement problem in its purest form. And it's at what point does the quantum blur become a classical fact? Is it when the Geiger counter clicks? When the vial breaks? When the cat dies? When you open the box and look? When a friend asks you what you saw? Quantum mechanics, the bare mathematics, does not answer this question. It gives you the superposition and shrugs. Well, the honest answer is, we don't know. Not really. This is called the measurement problem, and it has been open since the 1920s. Every interpretation of quantum mechanics has a different answer. The Copenhagen interpretation, which is the one most textbooks teach, says, don't ask. The wave function collapses when you measure, and that's that. Don't look for a mechanism. There is no deeper story. Just accept the rules.